Moving on to electrolytes. We will talk about electrolytes all over the place in anatomy and physiology. Electrolytes are simply salts, which is another term for a specific set of ions that, when placed in water, become ionized. They become this charged state. They're going to form solutions that are able to conduct electricity. So it's not just pure water. It's not water with iron in it. It's not water with copper in it. We're able to pass an electrical charge through it. The body has a slew of electrolytes. Off the top of your head, you're probably going sodium chloride. Both true, both valid, but it's got a slew more. Some other abundant electrolytes in the body are going to be calcium. Calcium is considered an electrolyte. It's not just for your bones. If you've taken a physiology class already, or you happen to have my med term, you have heard me talk about this. Calcium is not just for bones. Calcium is important for nerve conduction. Calcium is important for muscle contractions. It's really, really important. Then we have magnesium, also an abundant, important electrolyte. We have, I am forgetting their actual names, but these two molecules right here, which are also super abundant, so I need to remember them. But I'm spacing their names right now, even though I just talked about them the other day in another class. All of these, having an imbalance of them, is going to cause a range of side effects, ranging from muscle cramps to brittle bones, all the way up to coma and death. So very, very minor, very fixable to unfixable. Bicarbonate. Aha. So this guy right here, HCO3 minus, that is bicarbonate. This guy here is, it's not phosphate, it's forget its actual name, but does have phosphorus in it. All right, another thing we hear people talking about is free radicals. Free radicals are simply a particle with an odd number of electrons. So it's simply a free-floating particle that has an odd number of electrons in it. So, for instance, an oxygen molecule with an extra electron is the most commonly talked about one. Why is this important? Well, these super electron oxygen molecules can interfere with other reactions. They can interact with other molecules and trigger chain reactions that eventually destroy molecules that we do need. So how are they created? Honestly, we make them ourselves all the time. They can be a byproduct of metabolic reactions, radiation, various chemicals that we ingest. So then, what is an antioxidant? An antioxidant is something that neutralizes these electrons. They neutralize these free radicals. They do that by taking away this electron. My brain got ahead of my words. So, what are some antioxidants? Well, from nutrition, you've heard of some of these: vitamin E, carotenoids like vitamin A, and vitamin C. Vitamin C is a huge antioxidant with a lot of different benefits, but one of them being that we can take high doses of it every single day, and we're just going to pee out the excess. So as long as our kidneys are healthy, we're good, which means we can make sure we have plenty of it, as long as we space it out through the day. There's another one called superoxide dismutase enzyme, SOD. Probably haven't heard about that one, but it's one that our body makes naturally to help neutralize these free radicals. Anytime you see anything here that ends in A's, it's simply referring to an enzyme. Hopefully you guys remember that from med term. So this enzyme right here is kind of redundant. We're just basically saying enzyme. Talking about some other elements here. One second, I'm making some notes as I go along here. So we have atoms. What is a molecule? A molecule is two or more atoms that have bonded together. Now this is covalently bonded, but this could be ionic bond too. A sodium chloride molecule is ionically bonded. It's still a molecule. And it does not have to be the same element. That being said, we tend to refer to some things as being compounds because they have two or more atoms of multiple elements. So we're starting to get these complex setups of these atoms and of various types. It's not just a one-in-one thing, it's like a two-in-one, like a water molecule, or it's like a glucose molecule, which is C6H12O6, 6 carbons, 6 oxygens, 12 hydrogens. That could be considered more of a compound versus a molecule. But honestly, we tend to just use the term molecule. All right, so we have three main types of bonds: ionic, covalent, and hydrogen. Ionic and hydrogen are relatively simple and straightforward. However, covalent bonds can get complicated because there's lots of subdivisions. So this table here on page 17 will be very useful because it gives you a Cliff Notes version of these things. So, what is an ionic bond? An ionic bond is when you have a weak attraction. Think of a weak magnet between an anion and a cation. So between a positive ion and a negative anion. They're attracted together like a magnet, but it's a weak, so you don't have to use a lot of oomph to pull them apart. And that's exactly what an ionic bond is. These bonds are easily disrupted by water because these compounds, these substances, are going to easily dissolve in water. I'm going to skip covalent bond and come back to it in a second. What is a hydrogen bond? Hydrogen bond is going to be a weak attraction again, so easily disrupted, between polarized molecules or polarized regions of the same molecule. Think of a water molecule where you have an oxygen and two hydrogens. The hydrogen is going to have a slightly positive charge to it, and the oxygen is going to have a slightly negative charge to it. That's called a polar bond. The electrons are not shared evenly. So there's a slight charge disparity in the molecule. So that slight positive charge of the hydrogen can bond with something else that has a slight negative charge. Potentially the oxygen of another water molecule. But that would be a hydrogen bond. Covalent bonds are when the electrons are shared between the atoms. So if I have an atom that wants to give up one electron and I have an atom that wants to take on one electron, that electron is going to spend time with both of the atoms. How it spends its time will determine if it's a nonpolar or a polar covalent bond. A nonpolar covalent bond is when it spends its time equally between the two atoms. A polar covalent bond is when it spends its time more with one atom versus the other. My water molecule that I mentioned. The electron spends more time with the oxygen than it does with the hydrogen, giving it a slight charge. Now, Single and double covalent bonds are simply referring to how many electrons are being shared. There's also, I've seen triple covalent bonds. So a single covalent bond means only one electron is being shared. Double covalent bonds mean 2 electrons are being shared. And then the triple electron or covalent would be 3. That one's not that common. Most of the time you just see single and doubles. So here's an example. I have sodium and chloride. They're not sharing, it's literally giving it up. It's letting an electron come over here and it's staying over here. Here's our covalent. Now, this right here, this is a good exercise for you to do. You can Google image a chloride molecule, that's the Cl2, and an oxygen molecule, O2. Find and draw a water molecule, and then look at and trace in these with these molecules, Cl2, O2, and water, if they're polar, nonpolar, the types double or single covalent bonds, things along those lines. It's a good exercise. Grab a piece of scrap paper. Here's our single covalent bond. Here's a double. This is carbon dioxide, actually. We have an oxygen double bonded to a carbon, and we have another oxygen double bonded to a carbon. So this carbon is actually sharing in total 8 electrons. Here's our nonpolar versus polar. You can see this slight charge because they're unequal to be shared. And here's our hydrogen bonds. So everything that I already mentioned. And here's an actual image of that. Water itself, the water molecule, is a covalently bonded, a nonpolar covalent bond molecule. But the bonds that water molecules form between each other are going to be hydrogen.